Hi, hello, welcome to section 3 of chapter 6. Here we are. Finally, this is where we need to be in this chapter. And I said this is the most crucial part of this chapter and it can get a little bit tricky. As you see here, lots of rules. And I have made these, or I use the textbook rules and wherever that I feel like, I need little bit extra clarification for the students so that they don't confuse. I added lots of extra wording and I feel really good about it. It's almost kind of foolproof. In trying to draw Lewis structures, it kind of covered almost all issues that would come up when you try to draw Lewis structures. So please use the rules when you try to draw Lewis structures. Today I'm going to show you in this lecture how to draw Lewis structures, which is kind of a bread and butter for a chemist, at least for organic chemist. If you're hoping to be, well, not just organic chemistry and also in other science, biological sciences like in biology or biochemistry, anatomy, physiology, all of these sciences also would use chemistry structures. So if you are one of those students that are leaning towards biological sciences, you really need to know these topics as well. So it just gives you complete perspective that you really need. So what are we doing here is we're trying to come up with the chemical structures like you're seeing here. Here is a carbon connected to 4 hydrogens. We are going to talk today how to draw these kind of structures by yourself, or maybe this structure, carbon double bonded and there are hydrogens on both sides. How do you come up to that structure? Or this structure where oxygen connected to hydrogen to form water, or this structure like nitrogen connected to 3 hydrogens to form ammonia. How did we come up to these structures? So by the end of this lecture, you will be so proficient in drawing Lewis structures that if I give you a chemical formula, you are going to be good at drawing the chemical structure by yourself. Okay. So I just had these rules, but I actually have them differentiated in 2 different pages so that it is easy to read for you. So because there are a total of 9 rules. So let's read from here. So it is easy to read for you. I have 4 rules here and rest of the 5 rules on the next page. I'm going to briefly go over them now, and also I'm going to go over all of these rules when I try to show you when I'm going to show you the practice of drawing Lewis structures. I'm going to go each one of these rules again and again. I cannot I cannot stress enough the importance of following the rules when you try to draw Lewis structures. Everyone, no matter how genius you are, you have to kind of start from the scratch. And after a few days, or maybe after this term, you don't have to reuse this. You kind of go with your, intuition flow. But if you're just exposed to it, you must follow the rules. Otherwise, you're just setting yourself for a lot more frustration later. We don't want you to, we don't want you to confuse yourself. And these are the rules that you must follow when you try to draw Lewis structures. Please, please, please do not try to take shortcuts with Lewis structures until you get really good at it. You will, trust me, you will get really good at it. But until then, you need to trust me to not to take shortcuts. I have to say that I, as a organic chemist and having a PhD in organic chemistry and with a love and heart for the organic chemistry, I love these topics, this chapter and next chapter, and they were so close to my heart. And also, I'm really good at explaining them too. So trust me, I know what I'm doing. Please follow the rules. And I have had students that dropped out of general chemistry class in the first term because they were exposed to these topics and they were not making sense for them. And that's what happens for many students. They kind of drop out of this general chemistry class when they were exposed to this material because it gets so complex if you didn't get the right explanation. if you didn't get the right guidance. I have had so many of those students taught by me, either by tutoring or in my classes, that dropped out of another classes but got into my class, and they were so successful after following these rules and following my method of teaching. So yeah, again, please follow the rules. Okay. See what are the rules, why I'm stressing this. So there are a total of 9 rules that covers all possible variations, or I should say only 8 rules. Rule 9 is kind of caution. So the first rule is that you need to be able to not you need to count the total number of electrons present, total number of valence electrons present, and all those valence electrons together for a given molecule. And if at all you were given a charged element, you need to add an electron for negative charge or subtract an electron for positive charge. Again, if they're not making sense right away to you, that is normal, because I'm not showing you any structure. I'm just trying to read them. That's why I'm not going to spend a whole lot of time on it, because without showing you the structure, it doesn't make sense to you. It shouldn't, right? That's why I'm just going to go over lightly over them. And when I practice the structure, I'm going to go in detail. So you need to know the valence electrons, right? Valence electrons, how do you calculate? Group number is a good indication to tell how many valence electrons an atom is going to have. So let's say if you have water, right? Let me quickly show you an example. If you had a water, hydrogen is from group 1, oxygen is from group 6. So there are 2 hydrogens, 2 1 electrons, 2, and 1 oxygen times 6, total 8 valence electrons in water. That is how you would calculate. Okay, and once you do that, in step 2, draw a skeletal structure of the compound. This is the important step. It's like the foundation, and you need to make the right decision here to identify the crucial part is identifying the central atom, which is going to be the central atom. That is the key here. The least electronegative atom is usually the central atom. The central atom, because central atom is the one kind of foundation like a molecule. It connects with most of the atoms that are present in the molecule. So you need to choose the least electronegative atom, which happens to be the least electronegative atoms can make most number of bonds. We are talking about non-metals. You know that fluorine is most electronegative compared to oxygen, but oxygen can make 2 bonds, fluorine can only make 1 bond. That's why if you go with this clue of least electronegative atom, you would end up with atom that can make most bonds in a molecule. So that is going to be the wise step. Okay, and until here it goes smoothly, but sometimes you would have to choose an atom that has not much significant differences in electronegative values, or that can make same number of bonds. That is why I added this. Look out for the elements from period 3, 4, and 5. They were kind of, comes under exception towards the end of the chapter, but again, I want to include these rules for every possible exceptions, kind of made this one rules as a foolproof method rules. There are cases when group 3, there are cases when elements from period 3 or 4 or 5 would try to make more bonds than they would normally from that period. What it means is fluorine all the times makes only 1 bond, which is from period 2, but chlorine or bromine or iodine, which are from period 3, 4, 5, will make a 2 or 3 or 4 or 5 bonds. Well, not 5, 4 bonds easily. Because of the d orbitals they have. We are going to talk about it at the end of the lecture, at the end of the chapter. Why is that? I will go over the details. And in rule 3, for each bond in skeletal structure, once you draw the central atom and try to connect the atoms towards it, and you need to subtract the number of atoms that are used for bonding electrons together, for bonding atoms together. So you kind of identify how many electrons you use for bonding, you subtract from the total number of electrons you find from step 1, and the difference you use it as in the form of lone pairs. Again, I'll go over all of these details pretty soon when I have a specific example. And then use the remaining electrons to complete the octet number of electrons. See, this popped up. This is the most important rule that you have to must satisfy. you need to make sure all period 2 elements and all other elements except hydrogen has 8 number of electrons in its valence electron. Then only you're correctly following the Lewis structure. Otherwise, something is going on wrong. So you need to give the electrons to the outside elements to make sure you have the octet number of electrons. Number 5, place any remaining electrons in a pairs on the central atom or on the remaining least electronegative atom. You will have to do that. Again, I'm going to show you specific examples. And step 6, if the central atom has fewer number of electrons, there is a case when you will have a fewer number of electrons available, but you left with not following the octet rule for your central atom. That is when you would start making multiple bonds. Remember, I showed you multiple bonds, like double bonds between atoms, triple bond between atoms. This is why there are multiple bonds exist, because some atoms do not have octet number of electrons, and no more electrons, no more valence electrons available for making making everyone had octet number of electrons. That is when you start sharing multiple bonds. And then you would count all the electrons in the Lewis structure to confirm the use of total valence electrons available, just like, cross check. And then if something is, wrong, you would have to go to previous step. If not, in number 8 and number 7 is not really a step. It's like, cross checking your work. And number 8 tells us that when you try to draw a Lewis structure, you have to draw a Lewis structure that is electronically neutral, if possible, or try to write a Lewis structure that has the least possible charges. We are going to talk about it, how to do that, because charges mean that more reactive. So that's why we try to keep the charges low possible or neutral if at all possible. That's why we try to check if you manage to get a Lewis structure that has the least possible charges. Okay. So kind of like 7 and 8 and 9 are not really steps. Until 6, there are the steps, and 6, 7, 8, 9 are kind of like, checking for the correctness. Okay. All right. So just to remind you, this is the electronegativity chart that you would have to refer, because in step 2 you need to choose the central atom. The least electronegative atom is going to be your central atom. But hydrogen cannot be the central atom, because if you remember in the first section of this chapter, I showed you that hydrogen can only make one bond because it only had one Lewis electron dot valence electron. So that's why it cannot be central atom. It has to be outside. Okay, let's go and practice this structure. We are jumping right with the challenging problem, ClO3 minus. See, not an easy problem. But this is a great example to practice all maximum 6 steps. That's kind of what we need, to walk you through these drawing Lewis structures. Okay, you are given ClO3, and this is what I need you to do. I need you to, I already showed the work. This is what you have to do. You have to calculate the total number of valence electrons, like exactly how I showed here. Okay, how do you do that? You identify how many valence electrons each one of those elements has by following the group number. Chlorine has 7 valence electrons. There is 1 chlorine atom. Oxygen has 6 valence electrons. There are 3 oxygen atoms. And there is a negative charge. Whenever there is a negative charge, you add 1 electron extra. So total happens to be 25 plus 1, 26 electrons. There are total of 26 electrons that you need to show when you draw Lewis structures. They can be in the form of bonds, a single bond, double bond, or a multiple triple bond, or in the form of lone pair. It doesn't matter, but you have to show all 26 electrons. You're kind of responsible to show 26 electrons on a Lewis structure. That is going to be your job when I ask you to draw a Lewis structure. Okay. Excuse me. So step 2. So in step 2, you need to draw the basic frame of a Lewis structure. Your basic frame of a Lewis structure has a correct, reasonably correct central atom. You need to have a central atom that is the least electronegative, so that it can accept more bonds. So between chlorine and oxygen, if at all, here is where it gets things complicated. If it is, elements from period 2, like carbon, nitrogen, oxygen, and fluorine, it is easy. You chose carbon over nitrogen, and you chose nitrogen over oxygen, and you chose oxygen over fluorine because they were all from same uh, period 2. However, if at all you happen to have atoms from period 3, 4, or 5, they would make more number of bonds than normally from elements from period 2. So you have a chlorine and oxygen. This is the trickiest example. This is the most challenging example. But we have to, discuss these examples because here we are in general chemistry, right? So between chlorine and oxygen, think which one is more electronegative. If you check the chart, you would find that chlorine has the electronegative value of 3, oxygen has the electronegative value of 3.5, which means chlorine has to be your central atom. Okay, how do you know how to choose? Here, it is where I'm included. Look out for the elements from period 3, 4, 5. They can make more bonds than usual if needed. You think that, oh, chlorine is from period 7, it can only make one bond. But the first rule I'm saying is choose the least electronegative element. So you are choosing the chlorine as your least electronegative element with 3.0 electronegativity over 3.5 to be the central atom, right? But from what you know, element from group 7, like chlorine, can only make one bond so far. But elements from period 3, period 4, period 5, like chlorine, bromine, iodine, have the ability to make more bonds if needed. Why? Because in the period 3, you not only have 3s and 3p, you also have 3d orbital, an empty 3d orbital. So if there are more electrons, they put those electrons in d orbital. Bromine also had 4d orbital. If there are more electrons, they put those electrons over there. Iodine has 5d orbitals. If there are more available electrons that it needs to accommodate, it puts those electrons in 5d. And it is not just chlorine, bromine, iodine. Sulfur can make more bonds than 3, like even if it is from group 6, where it's supposed to normally can make 2 bonds, and phosphorus, which is from group 5, can make more bonds than 3. Unlike nitrogen, sometimes they make 3, but if there is a demand to make more bonds, look for these elements from period 3, 4, 5, where they can use those magical empty d orbital shells to make the most bonds. Okay. Now that you know how to choose the central atom, this is the most complex problem, but we are dealing with the complex problem right away, and I will take you back to the easy problems later, because you kind of need it to cover all 6 rules, okay? So that's my central atom, chlorine, and I'm connecting all oxygens to the chlorine because I get a good feeling like these oxygens, if they're connected to the chlorine, you get a uniform structure instead of weird structure. You can try if you want to connecting 2 oxygens together instead of having 3 oxygens on it. You will end up coming back to yourself when you recheck step 8 that, oh, you have unnecessary charges. That's why we didn't go with the oxygen and oxygen connection here, even though technically you can, because you would most likely end up with the charges that you are not supposed to. So this is the best possible distribution. How do you know? You kind of get a feeling for it once you work with a few problems. Okay, this is kind of that feeling that chlorine is central, oxygens are connected. Now draw Lewis structure for, well, it's the same problem, sorry. Step 3, what did we discuss for step 3 is, for each bond in skeletal structure, subtract 2 electrons from total valence electrons, okay? Excuse me, and convert the remaining electrons to lone pairs by dividing with the 2. You already know how many valence electrons you have in the step 1, which is 26 electrons. Now you are going to take away the electrons that you use for bonding between chlorines and oxygens, and then find out how many lone pairs they could make up to. So those could be because you made 3 bonds and each bond is what the 2 electrons, you used 6 electrons, and 26 minus 6 is 20 electrons, and 20 over 2 is equal to 10 lone pairs. You have 10 lone pairs now. And we are going to work with lone pairs from now on, from step 4. By step 3, you should know how many lone pairs you are going to work with. Okay, these lone pairs, can be converted to bonds again later, but step 3 should end with identifying how many lone pairs maximum you are going to work with. Now in step 4, you're going to use these lone pairs, the 10 lone pairs that you identified, to make sure all the, I shouldn't say all the, that's where I get into trouble. You should make sure the most electronegative elements will get the octet number of electrons first. Okay, it's very picky. The rules are very picky. That is how you would end up with the right structure. Between chlorine and oxygen is more electronegative element. Okay, that's why you put chlorine in the center, oxygen in the outside. Now you made a basic structure of chlorine with the 3 oxygen bonds, and you recalculated how many electrons are unused, 20 electrons, which means 10 lone pairs. Now we are saying that use those lone pairs to make sure the most electronegative atoms get the octet number of electrons first. Why? Because we already know the most electronegative atoms are demanding. They love to have extra electrons. They kind of demand, even if you don't give them, they make the atom destabilized. They kind of, don't want to part of molecule if they don't get their, if they don't get their first dips on the electron pair. So that's where the most stable structure leads to. That's why we give these lone pairs to the most electronegative oxygens. In this case, happen to be oxygens, but the outside elements. Okay. Excuse me. Yeah. So we have that basic structure. You use 2 electrons, and sorry, you used 6 electrons already. You left with 20 electrons. 20 electrons are equal to 10 lone pairs. And we said that we are going to give it to outside elements first to make sure all of them has octet electrons. Currently, because there is a bond for each oxygen currently has 2 electrons. So how many more lone pairs each one of them need is 3. That is how they would reach 8 electrons, the octet row. So let's give 3 lone pairs to each oxygen. So you give 3 here, you give 3 here, you give 3 here. So it looks like you used a total of 9 lone pairs. How many we actually started with? 10 lone pairs. But this is what you have to do by the end of this step 4. You should try to give the lone pairs to all outside elements only. Okay, hold on that. Then we are going to step 5. In step 5, we are going to place the any remaining electrons. Like in this case, we left with 1 remaining electron. Only in step 5, you are going to place these any remaining lone pairs of electrons on the central atom to give the octet number of electrons to the central atom. So we are going to take care of the central atom in only step 5 to make sure it has the octet number of electrons. So you left with the 2 remaining electrons here, and central atom only has 6 electrons currently with 3 bonds. So you are going to give it as the step 5 says, and the central atom has the lone pair, and it has the total of 8 electrons as a result. So step 5 is satisfied. You did what you're supposed to do in step 5. Let's see in step 6. Okay, let's see if we have to go on or not. In step 6, if the central atom or any neighboring atom has a fewer than 8 electrons, then move one or more lone pairs from the outside element, the most electronegative element, to inside. Let's see if it is needed. Is it needed here? Here, it is not needed because this one already had 8 electrons. If it doesn't have 8 electrons, the rule says that move one of the lone pair in the form of double bond, but you don't have to do that. So you kind of don't have to do anything after step 5, but you don't know. until you check it. That's why we are checking it. So you're done with writing Lewis structure. You already got the Lewis structure by step 5. This is how you should follow. Sometimes your structure doesn't end in step 5. You have to use step 6. Then you have to make sure your step 7 is followed, which I'm going to do now. Even if you don't have to do anything in step 6, you just need to make sure you end up with the number of electrons you started with. We started with 26 electrons, if you remember. Let's count if we have those many electrons. 3 lone pairs on each oxygen. So there are 9 lone pairs, 9 times 2. 1 lone pair on chlorine, so 18 and 2. And there are 3 bonds, 3 times 2, so 6 electrons. And we have a negative charge, so 18 times, not negative charge, because I'm calculating how many are there on the structure. So there are 26 electrons. So you started with 26, you got 26. And I put negative charge here because it is the overall charge. I'm going to talk in section 6.4 how to calculate that charge. For now, just focus on how to draw Lewis structures. Section 6.4 is where we calculate the formal charges. All right. Okay. So this problem I'm expecting relatively easier than the previous one. So let's try to draw Lewis structure for CS2. You know, if you're confident, you can start, practice drawing Lewis structures on your own for this one by pausing the video. But let me work through it. So in step 1, your goal is to identify how many total valence electrons are there. In CS2, carbon has 4 valence electrons, sulfur has 6 valence electrons. There are 2 sulfurs, so a total of 16 valence electrons. Then in step 2, if you remember, I need to choose my central element. There's a carbon and there is a sulfur. So there are 2 kinds of rules we have to use. One is least electronegative element, and one is the one that can make most number of bonds. The one that can make most number of bonds is the one that you should give the first priority. If not, then the least electronegative element. So between carbon and sulfur, carbon can make most number of bonds, and also it is the least electronegative of both also. So it works both ways. So carbon is going to be my central atom. It is least electronegative as well as can make most number of bonds. So that's the basic structure. Obviously, sulfurs that has the less number of ability to make bonds, if they connect to carbons, your structure is going to end up nicely instead of connecting to sulfurs. Again, you get a feeling for it. If you make mistakes, you would know the right way to do after making few mistakes. So what you have to do in step 3, you need to calculate how many electrons are used in the basic structure of CSS. You used 4 electrons, you would count that, and you would subtract those 4 electrons from 16. You would end up with a total of 12 electrons now, which are equal to 6 lone pairs. And you would use those 6 lone pairs to give the octet to outside electrons. So 1, 2, 3, 1, 2, 3. So you have octet electrons on sulfur, octet number of electrons on sulfur. So step 4 is satisfied. I didn't like the next step that I have in the animation is already showing the complete structure. That's why I'm drawing it myself. So in step 4, you would give the lone pairs of electrons to outside elements to give the octet. Then in step 5, you try to put any remaining electrons on central atom, but you don't have any. So this is step 4, okay? And step 5, do you have any remaining electrons? No, I only had 6 lone pairs of electrons to work with, and I gave all 6 to 2 sulfurs. So I don't have anything to do on step 5. So go to step 6 now. Step 6 is that, okay, if your central atom doesn't have octet number of electrons like our carbon, it only had currently 4 electrons, then you're going to start making multiple bonds from the outside elements by converting the lone pair to a double bond. So we are going to convert this lone pair to a double bond that makes 6 electrons on carbon, And we are going to convert one more lone pair to a bond. That is going to make carbon double bond sulfur, the lone pair, and carbon double bond sulfur, and a lone pair. Okay, what does the step 7 say? Step 7 says count all the electrons just to make sure you used all the electrons that you started with. There are 4 bonds, so 8 electrons. There are 4 lone pairs, 8 electrons, 16. So sounds good. And step 8 asking us to look for if the molecule is charged or neutral. Currently it is neutral because carbon is supposed to have 4 bonds. It has 4 bonds. Oxygen is supposed to have 2 bonds and sulfur is supposed to have 2 bonds and 2 lone pairs, which it does, which means we are good. We come up with the correct structure. Okay. Yeah, I'm gonna skip this because I already showed you the work. All right. Now, this is what I'm going to do. I'm going to ask you to just give me a second. I'm going to what are those molecules? CH4. I'm going to pause the video and come back to you in a second. All right. So I am going to ask you to draw the Lewis structures on your own for these following molecules by using the rules. CH4, CCl4, H2O, O2, Cn-. Pause the video and practice yourself. These are relatively easier molecules that if you follow the rules, you would end up with the right structure. But I am going to work on them now, but my expectation is that you're going to finish it before you see the video. All right. So let's work on the first problem. I'm going to show you the first problem. First problem is CH4. So CH4, I'm going to count the total number of valence electrons. Valence electrons it had is 8. One carbon has 4 valence electrons and 4 hydrogen had 1 hydrogen, 1 electron each. Total of 4 times 1 is 4. So total of 8 valence electrons. And I chose my central atom as carbon because carbon, even though it is not least electronegative, in this case, you have to follow which one can make most number of bonds. There are 2 things that you need to be flexible with. One of them is going to make sense. You either going to use the one that is least electronegative or the one that can make most number of bonds. So in this case, you cannot use hydrogen as your central atom because it only makes single bond, even though it is technically least electronegative. That's why we are using carbon, because you need a molecule that you can build on. You need central atom that you can build a molecule on. So carbon is your central atom that is connected to 4 hydrogens. In step 3, you will count how many electrons you used for bonding. You used all 8, so no more electrons. So you don't really have to worry anything for step 4, 5, and 6, right? There are total 6 rows. So we are good. Next problem is CCl4. I'm going to show you the work, but my expectation is that you beat me to solve this problem and made me proud. So CCl4, let's count the number of valence electrons on it. There should be 32 valence electrons. Between chlorine and carbon, you need to choose the carbon as your central atom because carbon is least electronegative, and also the second point in favor of carbon is it can make most bonds. So 2 things are working for the carbon. So carbon is your central atom, and obviously it has to connect to all chlorines because chlorine is from group 7, and unless in special circumstances it doesn't make more bonds than it should. So that's why chlorines are making single bonds with the central carbon. So how many electrons we used for bonding is 4 bonds, 8 electrons. So we use 24 electrons total. So you have like 12 lone pairs left. What you're going to do with is you're going to use the 12 lone pairs and start distributing to the most electronegative outside elements first to make sure they have the octet first. So each chlorine here had 1 each chlorine here has 2 electrons already from the bond, so you need to give total of 3 lone pairs to each chlorine. There is no, this one somehow it doesn't show lone pair. So each chlorine has 3 lone pairs each, which made sure it has octet rule on all the chlorines. And in step 5, in step 4 you use them, and in step 4 also you would check if you left with any electrons more to give it to central atom. You don't have to give any extra lone pair electrons to central atom in step 5, which means you're done with the structure. You don't have to make any double bonds in 6 also, because carbon already had 8 electrons. So you're done with the structure by step 4. So now let's work on water. I already showed you, sorry. So water has 8 valence electrons. Oxygen has to be the central atom because hydrogens and fluorines cannot be the central atom. So oxygen made 2 bonds with the hydrogen. So it used 4 electrons for the bonding. And as a result, it left with the 2 more lone pairs. And you cannot give it to hydrogens in this case, even though they were outside, because hydrogens doesn't need more than 2. It already had 2 with the bonding. So you are going to use those lone pairs to give the central atom in step 5, because you cannot do anything on step 4 for the hydrogens. They cannot take more electrons here. That's wrong thing to do, to give more electrons to hydrogen. There is no space for them to take the electrons. So you give the electrons to oxygen, and step 6 is not applicable for water because we just had a total 8 electrons on oxygen. So there is no chance for double bonds, okay? O2. O2 has 12 valence electrons, each oxygen 6. So 12 valence electrons. There is no central atom here. You don't have to have central atom if you only have 2 atoms. So one atom is connected to another. You used 2 electrons for that. 12 minus 2 is 10 electrons. 10 electrons over 2 results in 5 lone pairs that you have to work with. Is it 5? Yes, 5 lone pairs. And you're going to give octet to 1 oxygen first. So you gave 3 lone pairs here, has octet, and this one only had 6 electrons now. So in this case, what do you do is, because there is nothing you can do in step 5, because you don't have any more lone pairs to give to any other element, you skip step 5, you come to step 6, and you redistribute the lone pair to the other oxygen to make the double bond. That is how there is a double bond between 2 oxygen atoms in oxygen molecule. So last problem is Cn-1, and I want you to work it by yourselves. Let's see what you got. You should have a valence electrons of total 10. Carbon has 4, nitrogen has 5, but because there is a negative charge, you should add 1 more electron. So 5 plus 4 plus 1 is 10. So 10 valence electrons, only 2 atoms here, so no central atom issue. So C and N should make the bond, used 2 electrons for it. And as a result, you're left with 8 electrons. 8 electrons results in 4 lone pairs, and 4 lone pairs between nitrogen and carbon. Nitrogen should get the first dibs because it is most electronegative. So nitrogen gets 3 lone pairs out of 5, and carbon gets only 1. Oh, sorry, out of 4 lone pairs, nitrogen gets 3, and carbon gets only 1 lone pair. Now you cannot do anything on step 5 because you don't have any lone pairs with you to give it away. So step 5 is not applicable here, but step 6 is applicable because nitrogen is happy with 8 electrons, but carbon is unhappy with only 4 electrons. Now you would redistribute the lone pairs to multiple bonds until one of your period 2 element or another element has 8 electrons. So you're going to redistribute 1 lone pair to have 6 electrons and 1 more lone pair to have total of 8 electrons. That is how you would end up with C triple bond N with a lone pair around carbon. And don't worry about how you got this negative charge for now, because we are going to learn that in section 6.4. Okay. So just to review, what did we do in this topic? we learned how to draw Lewis structures. Okay, how did we do that? We did that by diligently following the step-by-step rules. So there are, to be specific, 6 rules that I want you to follow diligently. And if you make a right call in step 2, your structure will automatically fall in right place. So I want you to, practice getting a feel for choosing the right element. Now, if you have just period 2 elements only, like combination of hydrogen, carbon, nitrogen, and oxygen, and fluorines, carbon is going to be your central atom all the time because that is least electronegative. Let's say if you have combination of nitrogen, oxygen, and hydrogen, then nitrogen should be your central atom. Let's say you have combination of oxygen, fluorine, and hydrogen, then oxygen should be your central atom. That is how you should get a feel for it. Let's say you don't have carbon, but you have combination of these nitrogen, oxygen, fluorine with one or more of these period 3, 4, 5 elements. That's where it gets a little bit interesting. You kind of have to get used to know when to choose these period 3, 4, 5 elements like chlorine, bromine, iodine, phosphorus, sulfur to be your central atom. Most of the times, right? Most of the times that you have to make your, these, let me take these away. Most of the times you have to do that when you have these chlorates. Not many. What are chlorates? Is, if you have these kind of molecules, or BRO3, or IO3, or ClO5, or IO5, or something like this. These molecules are H2SO4. In this case, sulfur makes more bonds than just 2, or H3PO4. Now, not many, but once you know who they are, you would know how to choose the central atom like that. But other than this, everything else, follows smoothly. You just need to make the right call on step 2. Again, it doesn't come right away, even for, smart guys. And you need to go through the struggle of practice to get it right. I want you to, struggle, practice, make mistakes, and come back to find the right way and get a feel for it and get really good at it, because that's what you need to do in this general chemistry class to be successful. Because everything that we are going to discuss in next chapter is depending on your ability to correctly draw Lewis structures whenever I gave you a molecular formula. So I need you to already master drawing Lewis structures correctly before we start the chapter 7 topics. Okay, that's all for this topic. Again, my job is done here, but your job starts, and your job is much more harder than my job. Right? Good luck.